At the end of this video, you should be able to interpret data points in tables and graphs and recognize equations that summarize data, distinguish between conventions for abbreviating units and quantities, use dimensional analysis to check the validity of equations, and perform order of magnitude calculations. Chapter 1, Section 3, Mathematics and Physics. Just as physicists create simplified models to better understand the real world, they use the tools of mathematics to analyze and summarize their observations. Then, they can use the mathematical relationships among physical quantities to help predict what will happen in new situations. There are many ways to organize data. Consider the experiment shown on the screen here, which tests Galileo's hypothesis that all objects fall at the same rate in the absence of air resistance. In this experiment, a table tennis ball and a golf ball are dropped in a vacuum. The results are recorded as a set of numbers corresponding to the times of the fall and the distance each ball falls. A convenient way to organize data is to form a table like the one shown on the screen here. One method for analyzing the data in this figure is to construct a graph of the distance the ball falls versus the elapsed time since they were released. The graph on the screen here visually represents the gathered data from the previous experiment. Because the graph shows an obvious pattern, we can draw a smooth curve through the data points to make estimations for time when we have no actual data. The shape of the graph also provides information about the relationship between time and distance.
The shape of a graph can tell you about the relationship between sets of data. This graph shows a linear relationship. As the mass increases, the volume increases. This graph is similar to the linear graph except that it is not a straight line. It curves, becoming increasingly steep. This curve is characteristic of an equation in which one of the values is squared or raised to some power. This graph has a steep curve that approaches but does not touch the axis. This curve is characteristic of an inverse square. As one value increases, the other becomes smaller.
While mathematicians use equations to describe relationships between variables, physicists use the tools of mathematics to describe measured or predicted relationships between physical quantities in a situation. For example, one or more variables may affect the outcome of an experiment. In the case of a prediction, the physical equation is a compact statement based on a model of the situation. It shows how two or more variables are related. Many of the equations in physics represent a simple description of the relationship between physical quantities. The units in which these quantities are measured are often also abbreviated with symbols consisting of a letter or two. Most physics courses provide some clue to help you keep track of which letters refer to quantities and variables and which letters are used to indicate units. Typically, variables and other specific quantities are abbreviated with letters that are bold-faced or italicized. And the difference between the two is described next chapter, Chapter 2, Two-Dimensional Motion and Vectors. Units are abbreviated with regular letters as well, sometimes called Roman letters. Some examples of variable symbols and the abbreviations for the units they measure are shown on the screen here. As you continue to study physics, note the introduction of new variable quantities and recognize which units go with them. The tables provided in appendices C through E in the back of your textbook can help you keep track of these abbreviations. In many physics equations, a change in one variable will cause another variable to change as well. Sometimes two variables will be directly proportional, meaning that if one variable is changed by a particular factor, the other variable will change by the same factor. In the chapter Forces and the Laws of Motion, you will examine the relationship between force, mass, and acceleration, which is expressed as follows. Force is equal to mass multiplied by acceleration. As this equation shows, doubling the force will double the acceleration for a given mass, because force and acceleration have a directly proportional relationship. In an inversely proportional relationship, a change in one variable will be accompanied by an inverse change of the same factor in the other variable. Using the same equation as before, F equals ma, consider the relationship between mass and acceleration. If the force remains constant, doubling the mass will reduce the acceleration by half. When solving physics problems, identifying proportional relationships among variables can allow for an easy prediction of how a change in one variable will affect other variables within an equation. Although an experiment is the ultimate way to check the validity of a physics experiment, several techniques can be used to evaluate whether an equation or result can be possibly valid. We can also use the equation at the top of the screen here to describe the relationship between the variables in the experiment. Change in position, measured in meters, is equal to 4.9 multiplied by the time, measured in seconds, squared. This equation allows you to reproduce the graph and to make predictions about the change in position for any arbitrary time during the fall. To make expressions as simple as possible, physicists often use letters to describe specific quantities in an equation. For example, the letter V is used to denote speed. Sometimes Greek letters are used to describe mathematical operations. For example, the Greek letter delta is often used to mean difference in or change in, and the Greek letter sigma is used to mean sum or total. With these conventions, the word equation mentioned before can be written as follows. Y is equal to 4.9 t squared. The abbreviation y indicates the vertical change in a ball's position from its starting point, and t indicates the time elapsed. Suppose a car, such as the one on the screen here, is moving at a speed of 88 kilometers per hour, and you want to know how much time it will take to travel 725 kilometers. How can you decide a good way to solve the problem? You can use a powerful procedure called dimensional analysis. Dimensional analysis makes use of the fact that dimensions can be treated as algebraic quantities. For example, quantities can be added or subtracted only if they have the same dimensions, and the two sides of any given equation must have the same dimensions. Let us apply this technique to the problem of the car moving at a speed of 88 kilometers per hour. This measurement is given in dimensions of length over time. The total distance traveled has the dimension of length. Multiplying these numbers together gives the following dimensions. Length divided by time multiplied by length is equal to length squared over time. Clearly, the result of this calculation does not have the dimensions of time, which is what you are calculating. This equation is not a valid one for this situation. To calculate an answer that will have the dimension of time, you should take the distance and divide it by the speed of the car as follows. Length divided by time. In a simple example like this one, you might be able to identify the valid equation without dimensional analysis. But with more complicated problems, it is a good idea to check your final answer with the dimensional analysis before calculating your answer. This step will prevent you from wasting time computing an invalid equation. Because the scope of physics is so wide and the numbers may be astronomically large or subatomically small, it is often useful to estimate an answer to a problem before trying to solve the problem exactly. This kind of estimate is called an order of magnitude calculation, which means determining the power of 10 that is closest to the actual numerical value of the quantity. Once you have done this, you will be in a position to judge whether the answer that you get from a more exact procedure is correct. For example, consider the car trip described in the discussion of dimensional analysis. We must divide the distance by the speed to find the time. The distance, 725 kilometers, is closer to 10 to the third kilometers, or 1,000 kilometers, than it is to 10 to the second kilometers, or 100 kilometers. So we will use 10 to the third kilometers. The speed, 88 kilometers per hour, is about 10 to the second kilometers per hour, or 100 kilometers per hour. So we will divide 10 to the third kilometers by 10 to the second kilometers per hour to yield 10 hours. This estimate indicates that the answer should be closer to 10 than to 1 or 100, which would be 10 squared. The correct answer, 8.2 hours, certainly fits this range. Order of magnitude estimates can also be used to estimate numbers in situations in which little information is given. For example, how could you estimate how many gallons of gasoline are used annually by all the cars in the United States? To find the estimate, you will need to make some assumptions about the average household size, the number of cars per household, the distance traveled, and the average gas mileage. First, consider that the United States has about 300 million people. Assuming that each family has about 5 people and 2 cars, an estimate of the number of cars in the country is 120 million. Next, decide the order of magnitude of the average distance each car travels per day. Some cars travel as few as 1,000 miles per year, while others travel more than 100,000 miles per year. The appropriate order of magnitude to include in this estimate is 10,000 miles, or 10 to the fourth miles per year. If we assume that cars average 20 miles for every gallon of gas, each car needs about 500 gallons per year. Multiplying this by the estimate of the total number of cars in the United States gives an annual consumption of 6 times 10 to the 10th gallons.
Dimensional analysis and estimation help you to check the accuracy of your calculations. Suppose we are about to take a trip to a city 725 kilometers away. We expect our average speed to be 88 kilometers per hour. How long will the trip take? We first verify that we have set up the equation correctly by making sure the dimensions of the answer are what we expect. Only one combination of speed and distance will have the proper dimensions to give us the time. Does time equal speed times distance? No. Does time equal speed divided by distance? No. But since the dimensions of speed divided by distance worked out to 1 divided by time, we next try the inverse equation. Does time equal distance divided by speed? Yes, this equation gives the correct dimensions. To estimate the answer, we make an order of magnitude approximation by rounding each quantity to the nearest power of 10. We find that the trip should take about 10 hours. An exact calculation shows that the trip would actually take 8.2 hours, a number in keeping with our estimate and having the proper dimensions and units.
At this point, you should be able to interpret data in tables and graphs and recognize equations that summarize data, distinguish between conventions for abbreviating units and quantities, use dimensional analysis to check the validity of equations, and perform order of magnitude calculations.